Okay, welcome. What I want to do in this lecture is talk a little bit about how it all fits together, materials and sustainability, lightweighting, all those kinds of things, and how we can actually also change materials properties and how that's actually important in making everything work. Let me just make sure I got my pen going. Seems to be going, maybe. But anyway, here are the big ideas. Material is central in sustainability. If we use materials property, we can use less. If you use less, that's really the holy grail. You pull less from the ground, you move less stuff around, and that's really, I think, what the humans have to do if they're going to be more sustainable, is get around with less. If you're going to do less, you probably need to do better stuff. And to do this the right way, you want to do this with quantitative design and evaluation. And that is the essence of engineering, is being quantitative about what we do. And let me make sure I got my thing on, pen. There we go. I can draw again. And so that is the essence of what we want to do, is really be quantitative about things. And it's a matter of making sure we're doing not just good things, but really about the best things that we can do. And often our intuition fails us on what really is the right thing to do. I'll give you an example of that. So what I want to do is give you the idea that a life cycle analysis is something that you and your students can do. It's an important thing, and this is how we decide if things really are the right thing to do or not. And I'm going to give just the very essence of this. Again, you should be able to do a lot more. And it considers the production, use, and disposal or reuse of materials as we go through. And also, again, properties are important, and properties like strength, stiffness, and density, understanding these things, and excuse me, I'm just struggling with my microphone, trying to make my mini studio a little better here. Understanding on how those things work really is the key to making everything work. And then at the end, I'll also kind of say material strength, for example, is a property that can be manipulated, and it's manipulated very differently for both aluminum and steel, and I'll hit that at the very end, and this is something we could easily expand upon. So part of this is done. I'm part of this group called LIFT, Lightweight Innovations for Tomorrow. It's one of the first centers of the National Network of Manufacturing Innovation. The website is at lift.technology, not a .com, not a .edu, not a .org, but a lift.technology, the whole word. And this is part of the website that you would see. This is the technology page, and we're really developing a broad ecosystem with this, as it says down here. We have 6 pillars: melt processing, powder processing, thermomechanical processing, novel and agile processing coatings, joining and assembly. These are basically the way we manufacture stuff, particularly out of metals. And that's the way we're organized. There's also cross-cutting themes like sustainability, and then also there's a big outreach workforce part of this. I'm proud to be part of this. I'm actually the pillar director for novel and agile processing, and I've had a lot to do with the development of the center at Ohio State. And I should also mention it's not just at Ohio State, but this is a collaboration with University of Michigan, the school up north, and EWI. We're, again, really proud to be part of it. So let me kind of give you one example of how our intuition sometimes fails us. You often get the question, which is the grocery store, would you rather have paper or plastic? And the plastic bag has a bit of a negative connotation. We often think that the paper bag is the much more sustainable option. We all, I think, know that the best option, if we can take like a cloth bag and use it over and over and over, that's the best option. But if you just compare paper versus plastic, which is better? Well, if you do the math on it, and that's really what this is all about, that's what engineering is all about, is doing the math to really figure out if you're doing the right thing. It turns out kind of obvious that the plastic bag weighs a lot less than the paper bag, and it usually costs about a similar amount of energy to make a given mass of material. Since the plastic bag weighs less, it probably is more sustainable, and it actually is, and it takes less energy, produces less greenhouse gas, uses less water to make a plastic bag than it does to make a paper bag. Now, again, there's a lot of other things that go into this. Plastic bag, if you throw it into the ocean, it may not degrade for a long time. It could get ingested by fish, things like that. That's bad. Plastic bags are based on petroleum products. That's not so hot either. If you take paper and properly reuse it, which is seldom done, you can do better that way. Point is These are nuanced decisions. There's a lot of social and other factors that come in, and depending on what you're wanting to optimize, do you want to be best for the whales? Do you want to be best for CO2 usage? They're nuanced, but generally the plastic bag is going to do less environmental harm than the paper bag, but the best thing is don't use a new bag every time. Just use a durable bag and use it over and over and over, and that's always the best option. So that's one. Another one that I find kind of funny. This is the EcoForce 1 bicycle. And if you notice, it's why it's eco is it's made from a bamboo frame, and you can see from here to here this is bamboo, from here to here this is bamboo, from here to here this is bamboo. The rest of it, if you look closely, is metal, and yeah, it's kind of cool. It looks cool. I do have a little bike envy for this thing, but at the same time, it's not necessarily a really sustainable thing. Because it really doesn't use that much bamboo. You're pulling bamboo out of some jungle, you're shipping it across, who knows how it's made, and you're not really saving that much metal. There's still a lot of metal in this bicycle. So is it really sustainable or not? You be the judge. It is wicked cool. So we got to give it at least that. Bikes are also kind of interesting. Bikes come in titanium, steel, aluminum, bamboo, carbon fiber, and it's really interesting that also back in 1984, this was a big deal for bike geeks. Cannondale made the first aluminum frame. And if you know anything about aluminum, when you weld it, it tends to get really soft. What Cannondale figured out how to do is heat treat the entire frame so it didn't warp too much, and then they also would precision machine parts of it, and that gave you a really lightweight, cool aluminum bicycle. It turns out aluminum, steel, carbon fiber are all pretty close to on parity if you do it right. But material science is really at the essence of doing these things well. So what I want to do is go through a few more, continue this sort of high-level thing, see what sticks. Again, if anybody would like to expand on some of these topics, I'd be happy to work on this with you. And I'm going to borrow liberally from an approach developed by Mike Ashby at University of Cambridge, developed through the company called Granted Design. This is stuff that's been put out for open source use. And I'm not going to borrow completely from what they do, but I'm going to borrow very heavily from what they do. So this is really interesting. So remember our friend logarithmic scales, factors of 10 going up the scale here. So every unit here is a factor of 10. And what this plots here is annual world production of various materials, and it breaks them up. First on this is oil and coal. We pull an amazing amount out of the earth every year. 10 to the 9, that's a billion. Something on the order of 7 or 8 billion tons per year of oil and coal come out of the earth. That's a big deal. This is part of where global warming comes from, because what do we do with that oil and coal? We burn it, of course. We also use the oil and coal to make steel. We make nearly a billion tons, maybe about 500.5 billion tons of steel every year. Almost an order of magnitude less aluminum than steel, actually more than an order of magnitude less aluminum. And these other things as well, other metals. Plastics, we don't make quite as much of as we do metals on a volume or weight basis. The other thing we make an enormous amount of is concrete and asphalt. We produce a whole lot of wood. And then these things down here are important, but not nearly as important as some of those big drivers. That's what these logarithmic scales tell you. We can also look at where carbon release comes from. It turns out about a third of all the carbon released to the atmosphere comes from making stuff and processing materials. About a third comes from transportation. About another third comes from heating and lighting our homes and businesses and cooling them as well. And so again, what are the big things in terms of annual CO2 production? Again, steel, cast iron, aluminum alloys are a big deal. Concrete's a really big deal. Paper, cardboard, wood are really big deals. And these are really big drivers in our economy in terms of what brings CO2 out into the atmosphere. Mostly I'm just showing this as raw data, but if you're going to make a difference, you've got to deal with these big problems. So the way we deal with these big problems is we consider how these fit into a life cycle. And natural resources, we talked about this in the lecture when we talked about copper come out of the ground, we make material, a whole lot of energy goes in, a whole lot of feedstock goes in, and a whole lot of waste comes out. You deal with a process like making copper from ores or iron from ores. Less than 1% of what you mine is the actual material or metal that you're interested in. So lots of waste comes out, lots of energy goes in. These are big deals. Then you make a product out of that material. Again, energy feedstock goes in, waste comes out. And again, quite a bit. Not usually as much as you have in material production, but quite a bit comes out. You use a product, an airplane, a car. Again, energy, feedstock, things like petroleum goes in, wiper fluid, all those things go in. Waste comes out, CO2 into the atmosphere being the predominant piece of that. And then you get to the interesting part where what do you do with something at the end of use? Well, these days, the biggest thing you typically do end of life is you just simply landfill a product or possibly burn it. Those are options. Landfill, could combust it. Could also recycle things. That's a really nice idea. Or you might be able to refurbish and upgrade and do that again, and this is far more sustainable. This isn't generally the way we're thinking right now. It would be great if we did, but that's not quite typical. Might even be able to reuse things. Again, very sustainable option. The way we deal with all of this is through a life cycle assessment. And again, I'm going to give you just the very basic ideas, but this is something that I think is very accessible in an advanced high school setting, and to put numbers on this, put quantities on this, put units on it is really important, and I think really can give you an idea of where you save, where you don't save. So what we do in terms of developing guidance, and this is actually a very nice approach that Mike Ashby's put together. You kind of consider what goes on. You've got energy that goes in. You put in energy in making the materials. Again, usually that dwarfs what's done in manufacturing. You might have to transport those materials to the point of use. For example, if you make plywood in China and use it here, that actually happens. You actually produce a lot of CO2 in just transporting that plywood from one country to the other. And then during use is where usually there's a dominant amount of use. If you've got something like an airplane or a car, it's going to burn energy the whole time it's going. If you can reduce the mass of that airplane, reduce the mass of that car, it'll use less and that'll become more sustainable. And then end of life, you dispose, you recover. All of these things can be accounted for, and that's really the essence of what we want to do in a life cycle assessment. Again, one of the things that's important in this, a big part of this, is the energy embodied in the material. And again, just in the essence of giving you data, you may or may not want to do things with this. It takes remarkably different amount. Again, going from here to here is a factor of 100. It takes almost 100 times more energy to make titanium alloys on a per kilogram basis than it does cast iron alloys, maybe a factor of about 40 or 50. So that's really important. Aluminum takes a lot more energy than it takes to make steels. That's because the aluminum ore, Al2O3, it's very tightly bound, or bauxite very tightly bound. It takes a lot of energy to separate the aluminum from the oxygen. On a per kilogram basis, it takes a fair bit of energy to make polymers as well. Ceramics all over the map. Things like brick, plaster, and concrete, not so much on a per kilogram basis, but we make so much of this stuff that it actually can be fairly high up on the scale. And then hybrids, composites can be all over the map depending on how highly engineered they are. Point I want to make here is not that you should memorize this, but just recognize that data like this exists. There can be huge differences. For example, if you want to make something out of carbon fiber, you say, well, that's a way to really reduce vehicle weight. It takes a whole lot of energy to make that carbon fiber. It generally takes a whole lot of energy to make solar cells, to make things like batteries. And so if you use them a lot and use them properly, you can save a lot with them, but there's a big environmental cost in just making these things. That has to be accounted for, and that's the point of this, and the point is that there is this data out there, and we're not going to go much deeper than that. And get to here. So again, this is our strategy. We can do an audit, and then when we design things, we want to use the materials such we minimize the energy use, we minimize the energy in manufacture, we minimize the amount of transport. We minimize the energy in use, and that's a matter of good design. And then when we dispose, if we can, we'd like to reuse stuff rather than toss it out or burn it. And we can be quantitative about all this stuff. So, so we can consider a bunch of different things, and I'm just going to put them out here relatively quickly and go through just maybe 3 of these, maybe 4. To consider an aircraft, something like a 737. It turns out 737, if you do the math, burns in a massive amount of fuel. Every time that thing takes off, you have an hour-long flight, gets to 30,000 feet, comes back down, burns an enormous amount of fuel. A plane burns many times its weight in fuel over its lifetime. That use dwarfs everything down here. If you're making an automobile, it's not quite as stark. The energy required to make the materials is important. Again, if you use something like aluminum, you're going to drive this up. You might drive down the amount in use, but under certain circumstances, it can be a wash. We can be quantitative about that. If you do like in a refrigerator, it burns a lot of energy during use. Most of the time, if you put a little more money in insulation, you can drive that down, but you might drive the amount of energy used in making materials up. So there's balances in these things. If you take something like a car park, it's almost all in the energy that's required to make the thing. And again, as I showed you before, concrete takes a lot of energy to make. Again, I'll let you ponder these on your own. I think they make sense. It's a really nice, systematic way of making these decisions about what is and is not sustainable. So let me take this into lightweighting and mass reduction in vehicles, and what does it mean for you? So this is metrics. What is the proper metric for looking at a car? Well, the one that we often use is miles per gallon. And if you've got a car that does, say, 30 miles per gallon, you're doing pretty well. If I drive a school bus, it may only get 5 miles per gallon. But if I put 30 people in that school bus, the number of gallons of gasoline per passenger mile is much better than the bus. So passenger miles per gallon could be a better metric. The other one that I'm going to look at is how much energy it takes to take a bit of mass, an extra distance. So that's kind of an interesting thing. So, for example, if I take a helicopter, it takes me on the order of about 50 extra, what are my units here, 50 extra kilojoules to take 1 extra kilometer, 1 extra kilogram, an extra kilometer. Let me say that again. So for a helicopter, I might be on the order of about 50 kilojoules to take an extra kilogram, an extra kilometer. So if I put another FedEx package on a helicopter, take it a kilometer, it actually makes that helicopter work harder. If I put this on a diesel ocean ship, it hardly notices it on that scale. Again, logarithmic scales are good because these things are so terribly different. Personal autos are in the middle and so forth. Well, we can try to make sense of this way. These are my transport energies. This is kilojoules per kilometer per kilogram, and I can take these various things like a helicopter burns a lot of fuel, airplanes burn a lot of fuel, cars not so much, ocean freighters we do about as best as we do. Well, over the life of any of these vehicles, how does that help you? Well, I can look at the service life of these things. These long-haul aircraft, these things go millions, many millions of miles over their life. And if you multiply that by the transport energy, you can find out that these airplanes, if you pull out a kilogram, it'll save about 3,000 liters of gasoline. If I do this with an economy car, I might only save on the order of maybe 10 liters of gasoline by pulling a kilogram out. So you can turn this into dollars. And each of these guys generate a contour there. And these things up here, these guys up here, anything further out this way, you save a lot of energy by reducing the mass of your vehicle. And you can be very quantitative about that. Okay? That's the point. We can make quantitative decisions. And what that means is and it also kind of scales with the expense of these things also. And again, our friend the logarithmic scale, I can put on the top of this, I've got vehicles. Let's look at the top first. Up at the top, up here, we've got cheap bicycles, you do the math, these come out at about $3 or $4 a pound. Over-the-road trucks and cars come in somewhere on $10 a pound. If I get a really good bicycle, something like you might ride in the Tour de France, it might be $50 a pound. If I make a commercial jet, they come in at about $1,000 per pound. Just take the price of the airplane, divide by its mass, and satellites are even more expensive. Well, if you have something that's pretty cheap, a cheap bicycle, it's really hard to put carbon fiber in it, just because if I've got something I'm going to sell for $3 a pound, carbon fiber might be up here at $70 a pound. You're never going to make it. So this just shows that different materials also have different costs all over the map, and you're going to use the cheap materials on the cheap bicycles and stuff. Hopefully I'm not going too fast. Hopefully you're hanging with me. I'm mostly just trying to give you a lot of data, open your mind to these things, and show that there is an approach through this. I want to get back to materials, and that's really the key of all of this. So let's consider what a car has to do, and that's shown over in this column here. It's got to be safe, durable, lightweight, relatively quiet, handle well. What that means, as we go to cars, let me show a picture of a car. We'll skip ahead and then come back. So the way we really try to do this is we've got the passenger compartment here. What you really want to do is make the passenger compartment, that's the passenger compartment. Marketing people like to also call this the safety cage. So you take the safety cage and you try to make that so that it just plain doesn't deform, so that you don't collapse this on people no matter what happens. But these areas out front, you do make these so that they have controlled crush characteristics in front and back. So if you crash into something, this softens the blow, and that's really the way we do things. So this has to be as strong as possible. You want alloys that are as strong, or plastics or whatever, that are as strong as possible so this doesn't collapse on people. Then you want controlled crush front and back. And we can translate all that into materials properties. So what we want is our ideal materials for the safety cage are strong. If you want things that are going to be relatively quiet and handle well, that tells you have stiff materials. We also have to worry about corrosion. Low density is good because you get a lot more material per pound if you have a low density material. You like things to be low cost, and for sustainability you'd also like low embodied energy. So these are all materials properties that we can design with, and this is the way your students can go forward with this. Again, let's think about cars a little bit. In the old days, we made frames by ladder frames and basically make a frame and then put a body on top of it. That's the way it was done. Trucks are still made this way. If you look at the latest F-150, which is an engineering marvel in many ways, it's a steel ladder frame, looks something like that, and on top of that, they put an aluminum-intensive body, and there's also aluminum crush elements on the front and back, which protect the passengers that sit here in the safety cage, safety cell. Exotics work a little bit differently. This is a Lamborghini, has a carbon tub in here. This is what you might use for a track car, triangulated elements. This is a Lotus that's based on an interesting kind of a wishbone system. This is another Lotus Elise. This is basically aluminum extrusions largely that are glued together in rivets. Really innovative. Again, same sort of thing. We try to make this undeformable and have controlled crush front and back. So again, so if you look at this closely, and I urge you to on your own time, you see that around the safety cage we use the highest strength materials. These are strength values, and then front and back we often put somewhat weaker materials that have controlled crush characteristics, and this is all highly designed. The most interesting cars right now are highly multi-material. This is a VW concept car that was put together and is now produced in Europe. And you can see the mixture of materials. There's steel, there's aluminum, magnesium hardened steel, and you'd also use polymers where you can, possibly on outer facing. And this is all basically using materials where they give you the best bang for the buck. So structural composites are really light, but can be very expensive. Actually, a lot of embodied energy with them also. Hot stamped high strength steels have very high strengths. Use that to avoid intrusion in the passenger zone. Magnesium you can get very complicated shapes by casting it. it almost floats. It's a little denser than water, but very low density. But it has poor energy absorption. You don't want to use that usually where you're going to be crashed, but it's great for seats, instrument panels, and so forth. Aluminum is a great all-round player. It's about 1/3 the density, about 1/3 the stiffness of steel. So that's how we more or less decide what's going to go where. So again, these days what we do is we use a multi-material approach. You can see various materials there, stick them together. That's why you optimize the vehicle. So steel is interesting. We've used a lot of steel in the past, and strength is a fairly easy thing to change, both in steel and aluminum. And we can do this both with steel and aluminum. We've got very different mechanisms for doing these, and I put this out here. If you would like me to do another lecture on this at some point, I'd be happy to. Steel is strengthened by quenching austenite from martensite. This is something we do in the ASM camps regularly. Aluminum is strengthened very differently. We solutionize it at a high temperature, then we quench it, and immediately after quenching, it's very soft. Steel will be very hard, aluminum turns out very soft, and then we age it, meaning we put it back almost like in a pizza oven, let it sit there for a while, and it gets harder with time. There's very different mechanisms. This makes martensite, this makes very small particles. In both of these, this doesn't change the stiffness, and you can easily show this in a lab environment with beam bending. So a possible lab you might want to do is the following. We can easily develop something where we use heat treatment and cantilever beam bending to explore strength, stiffness, and density of aluminum and steel after heat treatment. The question we have is what changes after heat treatment and what does not. Well, it turns out that the stiffness does not change much, density does not change much, if at all, but the strength changes tremendously. So if we just take and basically use a C-clamp, take a cantilever beam, make a beam of the same dimension of steel and aluminum, we can measure the yield strength just by measuring the force that's required for yielding, connecting that to these dimensions. And when you get permanent deformation, meaning when you start with a nice straight beam and then it turns out where it's got a bend right where the table connects, after you remove the load, you've passed the yield strength at that point. If you just take it so the force is small enough, you're not putting permanent bending on, we can also measure the elastic modulus through this formula. And the two properties we're interested in here, the materials properties, are the yield strength and the elastic modulus. The rest of these things are all either these dimensional constants, or D is the deflection here. So when I push it down, I get some deflection D, and that's that D in that equation. I put out as a question for you. I think this would make a nice lab. We can do this with steel and with aluminum, and that's where this could be taken. I don't want this to go too long, so I'm going to summarize here. Materials choice, processing design have major effects on energy use and CO2 production. Light metals can reduce energy use, but they can be costly to create, both in the sense that they can be expensive and they can require quite a bit of energy to put into them. And engineering is the key to making things sustainable. So with that, I'm going to end and bid you farewell. Hope to talk to you again soon. And let me figure out how to end this thing.